extra strong Roman concrete,
fully hydraulic,
structural solid connections.
It's the
structural
Engineering podcast.
Hello, welcome to the Structural Engineering Podcast. I'm Max.
And I'm Zach.
And this week we're doing a little in-between episode. I don't know, this is 21.5 maybe. We want to do an update on the Ridgecrest earthquake. We had the opportunity to talk with Maria Mohammed, SE. She is on the COSC board, and she was up at Ridgecrest and Trona shortly after the earthquake, inspecting some homes and stuff. So we had a cool opportunity to talk with her.
Yeah, it was nice that we had, Alex's opinion to go through what he saw and what his feelings were. But now to get the opinion of a licensed structural engineer, I'm pretty excited for you guys to hear what we got.
Yeah, and unsurprisingly, they're pretty similar stories from walking around up there. So we'll talk with her for a little bit, and then right afterwards, we're going to come back, and I want to talk about earthquakes in Japan. There, I think, is a lot of talk about how much better Japan is at handling earthquakes. It's like the German engineering or the Italian design. Those Japanese, they know how to handle an earthquake. But I figured we'd look into it ourselves, so that's coming up next.
All right, you want to say your tech tip?
Good point. And also, let's get a tech tip in there. So this is one I'm honestly not 100% certain on, and we were thinking about it last week, and I'm throwing it out there. I feel pretty good about it.
Throw it out there,
but
man.
This is seismic mass of snowdrifts. Almost always, this is not going to be a big deal. But as you may know, when the snow load is over 30 psf,
the flat roofs,
you've got to consider 20% of your weight in your seismic mass. But what about snowdrifts?
Drifts are not an infrequent occurrence, and often they can hang around for a whole season. So I want to argue there are a lot of cases where you might want to consider seismic mass of your drift. Not always, but in some instances.
What do you think?
I totally agree, and I think there's some really good examples of times where it could be quite substantial. And we were kind of talking about canopies, and man, you put snowdrift out on something like that. I mean, you're even just the percentage of snowdrift that you have to consider is going to be greater than the whole weight of the canopy. So
absolutely, yeah. Canopies tend to be very light, and if you throw a canopy on the edge of a huge warehouse, you have 200 foot of runway to collect a leeward wind drift. It can easily be 90 psf.
I could see someone arguing that it's not life safety, but what do canopies usually cover?
Cover the door, man.
They cover the exit, and that's something. I mean, a little off topic a tiny bit, but not much. But in all the earthquakes that were happening, or the big earthquake that happened in Alaska here this last year, that was one of the biggest things that happened was the exits were blocked. The structures were okay; they didn't collapse, but a lot of veneers failed. Specifically brick veneers, and landed in front of doors and blocked exit ways. So, it matters.
Yeah.
So if a canopy come down, that's a lot of weight.
Yeah. So get your drift seismic mass on your canopies. Probably. I'm gonna start doing it now that I thought of it.
Let us know what you guys think.
Yes, please do. And bonus tech tip: don't forget, parapets do not screen for snow drifting on things underneath them. So if you have a parapet up high that's collecting windward drift, you don't get to remove leeward drift from something below. I think that's in the commentary, but that's in there.
Let's call that the tech tip. The other one is the tech opinion.
All right. Well, let's talk with Maria.
So a couple people from my office and I went to Ridgecrest this Sunday after the earthquake. And EERI, I'm not sure if you've heard of them, the Earthquake Engineering Research Institute, they had put together a clearinghouse where basically all structural engineers, geologists, geotechnical engineers could just come together and exchange information. Yeah, it was pretty cool. And so we arrived to the clearinghouse and then met up with a few people who were planning on also doing reconnaissance, and got information from people who have done reconnaissance the day before on Saturday. And then we basically just decided to drive around and gather as much information as we could. So we started in Ridgecrest. Ridgecrest is a fairly new town. like I would say most of the homes were built in the 80s.
Nice.
You won't find like really older homes which you would think would be susceptible to earthquakes. So there wasn't really like a substantial amount of damage that you would expect from a city who just experienced a 7.1 magnitude earthquake, you know?
And I assume it's mostly very low rise, stick frame construction typically?
Yes, very light frame, single family residential. There were a couple hotels, kind of like Holiday Inn type of hotels, just 2-3 stories tall, but very low rise community. I would say most of the structure in Ridgecrest would be like a low period type of structure. So there wasn't anything significant that we noticed in Ridgecrest. We did end up going to the movie theater, which I think they only have one movie theater, and the owner wasn't there, so we didn't have access to go inside. But we were just curious because it tended to have really tall masonry walls around the perimeter, and it looked like it had some non-structural damage from what we could see through the windows. And if I recall correctly, I think some other engineers were able to go inside the following day and see that there was also like some ceilings have fallen down in certain parts of the building. But outside of, like a standalone instance, there wasn't like a significant extent of damage.
Interesting.
In
Did you get
Ridgecrest.
to go to Trona as well?
We did. So once we did reconnaissance in Ridgecrest, we went to Inyokern, actually. So Inyokern is slightly west of Ridgecrest, just because we were curious to see if there was any damage. And we didn't notice anything significant in Inyokern either. So we then headed to Trona. Trona was a very different case, and I think it might have to do with the age of the town. It's a very old town. Most of the single-family homes, you can tell, were built in the 40s and 50s, if not earlier.
The photos I saw look like there's a lot more masonry in Trona.
Yes. A lot of unreinforced masonry in Trona. Most of the single-family homes had brick chimney or like concrete masonry chimney. They had a lot of like unreinforced CMU block site walls, and the way that the town is also located right above what used to be a lake, I believe, there was quite a substantial amount of lateral spreading. You can see cracking in the road, buckling of the sidewalk. Like one part of the sidewalk would have either like rotated or slightly offset from the adjacent block of sidewalk. And most of the homes we drove by in Trona had some type of damage to their chimneys. Either the chimney like completely broke off or peeled away from the home. So there were a couple instances where it had fallen off of the roof, like onto the ground. A couple where it fell through the roof. So some type of like consistent damage throughout the chimneys that we observed.
Okay.
Trona seemed to have experienced more damage than Ridgecrest did. And I would say most of it has to do with the age of the town, age of construction.
Okay. Is the damage less than you would expect overall? I mean, based on the magnitude, it's pretty high, right? But it was a little bit deeper, and from what I found, the acceleration was about 0.4% gravity.
I'm actually surprised that the ground acceleration of 0.4 G, well, the ground acceleration was only 0.4 G for a 7.1 magnitude earthquake. And I hope geologists or geotechnical engineers are trying to explain that.
I'm not exactly sure what to expect as far as acceleration, but looking at Northridge or something was like 1.8 G, and that's a lower magnitude, way closer to the surface. But I mean, this is not my expertise by any means.
Yes, so we're kind of looking at the other discipline of earthquake engineering to help explain this to us. But given that most of the structures in Ridgecrest and Trona were low period structures, and it just having a high period earthquake avoided what would have been a lot of damage, I think. In terms of like, I guess, trying to quantify, is this the type of damage you would expect for this type of magnitude earthquake? I don't really know if this earthquake is a good conversation to have. I mean, a good example to have that conversation, mainly because the population of the towns that were close to the earthquake were relatively small. The number of buildings that experienced that level of shaking were very small. If that type of earthquake, a 7.1 magnitude earthquake, is to occur, say, in a big metropolitan area like LA,
totally different story.
Exactly. It's difficult to apply that experience to a different location. Yeah, and it is important to also note, I think you mentioned earlier in our conversation that you can't really design something to be damage proof. But it's also like the understanding the risk that we are designing to. The current building standard would design to what would be life safety standard, which mostly applies to making sure that the building survives the earthquake, and not necessarily the building remains functional after an earthquake.
Absolutely. And the damage you saw, does that sort of fit? I mean, there were no collapses, correct? This is just, I mean, cracks in masonry, but nothing fell down?
Yeah, like
right?
I would, there wasn't really like a house that pancaked.
Yeah.
The house that probably had the chimney fall through the roof, I would advise the residents not to just go inside immediately until they take the chimney out to make sure that there isn't a falling hazard or anything.
Certainly.
But there isn't anything that you would say is like a complete collapse.
Well, that's good to hear.
Yeah.
So Max, that was awesome listening to Maria there. I think she has some really good points, and just talking about the period of the earthquake and the structures and being load rise. I think it's really interesting and makes so much sense of why these didn't have a lot of damage to the structures. I think there is, like kind of she said, there's a lot of answers that we need to get from geotechnical engineers to understand
for more
what's going on with the soil.
Here. Yeah, it's pretty cool.
If you are listening and you are a geotechnical engineer, please reach out. We'd love to have you on the show. I think that's kind of one of the next, I'd say probably the next person we're going to be looking for to get on the podcast is geotech.
Well, let's debunk this Japanese stuff, or bunker. Figure it out.
I'm only designing with the Japanese code from now.
I only use Japanese steel. It's better.
Yeah, I mean, let's go through some of what they require differently than the U.S. and where we're similar in places. I think one of the first places we can talk about is the analysis procedure of the two different codes. So
Yep.
I would assume everyone listening is fairly familiar with how the U.S. code works. There's different analysis procedures, and there's times where you can use them, and there's times where you can't use them.
And you can pretty much always use ELF except for one case. And,
exactly. And then the Japanese code has like a very interesting like two-part analysis of it. I think it's pretty interesting. So you go through and design your structure using this first phase design.
And this one is allowable stress. I like how it's kind of broken up. Like this is elastic only allowable stress design.
Yeah, totally. So you know exactly how you're looking at the structure and how it's acting in that manner. And then you go to the second phase design, which is nonlinear pushover, nonlinear time history analysis, and is usually required to check the ultimate lateral strength.
And do you have to do time history analysis on every building, it seemed like? I don't know. This paper we both read, I mean, I didn't see that it was but it appeared that you run this set of 3 earthquakes, the golden trio, on every structure.
So it says for the second design phase is used when it's needed to check lateral system overstrength. Usually nonlinear static or dynamic analysis is required. The second phase design is not required for buildings up to 31 meters in height.
Okay.
So you're not talking a very tall building, 5-6 story building and beyond. You have to do the second phase of analysis and design.
I mean, in many ways, the code is pretty similar. If you're looking at spectrum response, they've kind of got two phases to this though too. They allow a higher damping ratio, and in there are two phases which you mentioned before. So they design for this allowable stress. They're designing to a moderate earthquake, and so their buildings have to survive with minimal damage in the elastic range, very low story drift, right? So like pretty much nothing is going to happen with a moderate earthquake. Then they have a separate earthquake, a severe earthquake, and that's what they're designing their higher buildings for. But the spectrum response looks very, very similar to what we're used to.
Oh, yeah. One thing I think is really interesting is the soil and site classifications for Japan and the U.S. I don't know about you, Max, but through all this studying it and kind of researches, it seems like the U.S. has a lot of options on about everything. And
yes.
And the Japanese code had like 2 to 3 for each category. We have A, B, C, D. We have a lot of site classifications. Japanese code has 3, and there's not a big discrepancy throughout the country because it's a small island.
Country. Yeah, it's probably much more homogeneous as far as terrain. So it makes sense.
So I think it totally makes sense to not have as much as the U.S. code does.
Yeah, but you're absolutely right. I do like their soil type classifications. They're much more they sound very scientific. Soils mainly from the tertiary era or earlier, or alluvium, mainly consisting of organic or other soft soil. Makes ours seem blunt, soft, less soft.
Right. They're trying to be way too generic in our code potential.
Yeah.
They talk about in here importance factors. So they also discuss the classification of buildings. In the U.S., we have from a category 1 risk category where it's super low hazard to human life to risk category 4, which is designed for essential facilities. In the seismic world, you increase your load by 50% on those structures. There's really nothing like that in Japan.
Yeah.
They don't classify a building as one, of 4 different elements. So I thought that was kind of interesting. There was no classifications for buildings based on occupancy in the Japan seismic code.
I don't know what to make of that.
I'm not sure either. It was an interesting fact.
Yeah, we'll leave it at that. I do want to throw in there, Japan has a lot of earthquakes. So I read that they have around 1,000 a day that you can feel. So for us, that's like over magnitude 2.5. They have a different scale. So if you see something, a Japanese earthquake that's above a 5 on their scale, that's huge. That's like a 7. It's more like the Mercalli scale, I guess. So it not totally parallel. It's more proportional to the damage that occurs than the actual magnitude of the quake. But 1,000 a day that you can feel, that's nuts. I got some numbers to be proportional here. So I found in 2005, they had 130,000 earthquakes. California got about 10,000. So, 13 times more. Yeah, and let's see. So California, for ones you could feel, they get a couple hundred a year above a magnitude 3 and 15 to 20 above magnitude 4. So, in order of magnitude higher at least on how many earthquakes you could feel. So I think the public perception also, which you talked about a couple times, is everybody knows that earthquakes are a big deal in Japan. So having your building designed for them is not a push for any, it's just how it is.
My other thought with that too is with that high occurrence rate of earthquakes, and they have quite some substantial earthquakes too. I would like to think that they also are thinking this on an economic scale. With that many earthquakes, they can't be rebuilding.
Yeah.
Part of probably what drives a lot of their seismic code is economics, and I think you brought this up previously, not on the show, but they have thousands of base isolated structures, where in the US we have nothing close to that.
Yeah, hundreds.
And so to me that's driving, maybe I'm reaching here, but to me that is like, okay, they're trying to be really efficient with their structures economically, is to not have to rebuild, not just for loss of life, but I think the economic gain of having structures. In the U.S., it's performance-based structures or design structures, which, you look a lot more at economics of that building. You don't want to take a big skyscraper and then have it go through a seismic event. It yields and you have to tear the building down, right? That's a lot of money that makes zero sense.
Yeah.
So I would like to imagine that Japan is thinking in that same direction with how they push to do base isolated structures.
Yeah, they're definitely progressive there. I mean, there's this great paper that compares U.S. and seismic design procedures specifically for base isolation. And they mentioned that in Japan, the board that reviews each of these projects is just the same. While in the U.S., the process and review members changes for every single project. When we're submitting something to the building official, if you're in a different location, it's a new building official. And they might have never seen a seismic isolated project. And in Japan, they just make that way easier by going to the same group of people every single time. And yeah, from what I read, it's a lot easier. Less strict guidelines. We require very high tolerance for the amount of deflection on a seismic isolated system. So what I mean, I guess, is a very high recurrence for the deflection that system needs to see. Japan has it a little bit differently, I guess. We look at the recurrence of the earthquake very similarly. So a 1 in 2% chance in 50 years, or about a 1 in 2,500 year probability for the design of the structure. But for the design of the base isolation, they do a 1 in 500 year. So a lower event. And then you're allowed to do a safety factor on top of that, but it just is a little less restrictive for the everyday earthquake, which makes it easier to handle. Should we wrap up Japan? This is a mini-sode after all. I think that kind of hits some of the bigger differences, at least as far as I understand from this one paper. We certainly didn't get too deep into this, but we just wanted to get a feel for the reality of how much better they are than us. They're better.
So in conclusion, what do you think?
In conclusion, they're more prepared for a low recurrence earthquake. I get the feel that we're on the same page for the 1 in 2,500 year event, 2% probability in 50 year. But yeah, for the everyday quake, I think that they are in a better position. And they get everyday quakes. We don't. So it's hard to really compare them side by side. Do we need to have that level of stand? I mean, it's too costly to design everything to stand up to a quake that doesn't happen every day.
I totally agree with you. The occurrence of which their earthquakes are happening so much higher than what we're seeing in the U.S. So it makes sense that their code is a lot different on what that occurrence interval is. But I don't think necessarily their buildings are better than the ones in the U.S. for the a like to like building. To close this out, I did some research on structural monitoring for seismic events, and I thought it was really interesting. In Japan, they have structural monitoring on everything. Yeah, like compared to the U.S., it's everything. In the U.S., I believe it compared it to L.A. The skyscrapers in L.A. only 3% of them have structural monitoring for seismic events. And that just blew my mind. Like, the monitoring is not that expensive, but can do
such a low-hanging
so much.
fruit. Hey, I wonder how much useful information you truly can. I mean, you can get the building's acceleration for research. I think it's great. I don't know. Is it limited? I'm not sure. I don't know enough about it, I guess. But it'd be nice to see it more places.
All right, guys. Thanks for joining us this week. As always, follow us on Instagram, Facebook. Send us emails. You guys reach out to us a lot, and we love it. The conversations are wonderful. More topics, comments, anything you got. And it means so much to us if you share this with your friends, your colleagues, anybody you think that would be interested in this. Please share it. We'll talk to you later.
See ya.